So that is my demonstration for rolling the can, making that nice magic trick. Excellent way to show some magic to a little brother or sister or some cousins, something like that. They usually really get a kick out of that. Anyway, that is our second kind of charging. Our third kind is charging by conduction. So this is when the object is actually in contact with the charged object and they end up with the same charge. This is kind of what happens when the pieces of paper end up on the comb. They do get the same charge as the comb. Sometimes the electrons will move onto the paper, and that's another reason why they jump off. So this is a Van de Graaff generator, and we've got this girl isolated from the ground. So I used to put my students on a big plastic stool that was, I don't know, about 18 inches tall, maybe 16 inches tall, and that isolated them from the ground so they would hold that static charge. So this Van de Graaff generator makes a whole lot of volts, 300,000 volts, yet it does not harm you because those volts are not going anywhere. Only time electricity harms you is when the electricity is flowing. So this is a static electricity. It is staying the same. And so since it's staying in the same place, there is no current and no zapping. So let me just show you how this works. So the Van de Graaff generator has a belt inside. That's this brown thing you see in there's a glass or plastic tube. That's the belt is in. And the belt is made out of rubber, so it picks the electrons up off of the metal dome on the top and it deposits them into the earth. So she gets on there and puts her hand on there before you turn on the electricity. So it's neutral when you start with your hand on there. If you don't have your hand on there, when your hand gets close, it gets charged by induction and it gets zapped, constantly gets zapped. So you want to start with your hand on there. And so all the electrons on your body and on her hair get pulled off and put into the Van de Graaff generator. So all your hair stands on end, pretty crazy. Back to our model here. So if we have a positively charged rod, and we bring that next to something that's neutral, especially things that are metal, are good at charging by conduction. So when those two things touch, the electrons are trying to repel the other electrons. It says, oh, look at all this positivity. I'm going to just jump over here. I'm attracted to all that positivity. And so those electrons spread out as far apart from each other as they can. So maybe half of them stay on the sphere and half of them go over onto the rod. What they've done here is they don't show any more of the electrons in the bottom picture, but there's fewer positive charges. That's because a lot of them got neutralized out by those extra electrons. So it's still positively charged, and now the sphere is positively charged as well. So that got charged through conduction. Here's a few more kids on the Van de Graaff generator. There's a video there of that, and you can get the video in the slides. The slides are in Canvas. So I like to put them in there in case you want to access them without going through the Nearpod again. And our real life example of charging by conduction is the car, when you drive your car. So when you drive in your car, those wheels are just like that belt in the Van de Graaff generator. They pull the electrons off the metal body of your car, deposit them into the earth, so your car becomes positively charged. You're in the car, so you get charged as well. However, when you get out, you step on the ground and you become neutralized. And then you go back to close the door and zap, you get shocked by the car. So what could you do to prevent yourself from getting shocked when you get out of the car? What do you think you could do? All right, our last thing today is electric potential energy. And what is it? How is it related to charges? Well, let's go back and talk about gravitational potential energy first. Think back to our unit on energy right before the IA. Right before momentum, right before the IA. And what was gravitational potential energy? Hey, it's a good time for a multiple choice question right here. So gravitational potential energy is that stored energy due to height. Remember, we calculated it as PE equals mgh. So what do you think electric potential is? Any ideas? So electric potential energy is stored energy due to one charge being near another charge. And usually we talk about them as being the same charge. So what do you think you could do if you had two positive charges? What could you do to increase their electric potential energy? And think back to how we could increase gravitational force, gravitational energy, similar to that. Number one, move them closer together. And number two, make them stronger. So increase the charge on there and then move it closer. So this is very similar to gravitational energy, gravitational forces when we get to electric potential energy and electric forces. So this is a few pictures here from Cartoon Guide to Physics. If you are interested in Cartoon Guide to Physics, the PDF of the book is in the Welcome Information module in Canvas. So here she goes. She's pushing that proton towards this guy's proton, and it takes a lot of work. She has to work to push those similar charges together because they definitely want to repel. And the work that she is doing is stored as electric potential energy. Before, we lifted something and it was stored as gravitational potential energy. That work done when you walked up the stairs was stored as gravitational potential energy. And then when you release it, boom, they repel, and that little proton goes zipping away. Same way, when you went down that imaginary slide, down your stairs, boom, that gravitational potential energy turned into zippy kinetic energy. She finally decided to join us. The last thing you want to do today is take a look at the CA2 practice review. We are taking the common assessment in class tomorrow, but we'll do it again at the end of class. So we'll review and practice and learn a little bit and then take the common assessment at the end of class. Thanks for watching. Thanks for Nearpotting. I hope you enjoyed the demos, and I will see you guys on the next time I see you. Bye.